example 5.8 from the textbook. We're returning to a skier on a slope, and we'll see what we can analyze now using our energy techniques. The setup this time is that a skier is starting out 20 meters high on a slope of some unknown angle, and on that slope there's no friction. This is a frictionless slope, really slippery snow. When the skier reaches the bottom of the slope, they are now traveling horizontally, and the snow is stickier, so there is friction at the bottom, at the horizontal portion of this motion. So we'll ask two questions. What's the skier's speed at the very bottom of the hill? And the second question is, how far does the skier travel before coming to a stop? And we can answer both of these questions using energy techniques. So let's look at the first question. What's a skier's speed at the bottom of the hill? Previously, we would only have been able to figure this out if we were given that angle, because we would have had to do Newton's second law on a slope, figure out the acceleration, and then use kinematics to figure out the speed at the bottom of the hill. But now that we know conservation of energy, all that's important is that we know the initial height and the final height. And using our energy analysis, we have our initial potential and kinetic energies, our final potential kinetic energies. They're equal to one another. We've got formulas for all these things. mgy initial plus 1/2 mv initial squared, mgy final 1/2 mv final squared. And the math is exactly the same as from the previous example, the roller coaster, where we saw that the answer for v final is square root v initial squared plus 2g y initial minus y final. And we know v initial in this case is 0, and y final in this case is also 0. We assume the skier started from rest and ends at ground level, which we'll call 0 height. So plugging in the numbers gives us a speed at this location B equal to 19.8 meters per second. So this is kind of cool. We didn't need to know the details of that slope. We didn't need to know the angle, just like in the roller coaster problem. We didn't need to know the shape of the track or the angle anywhere along that track. All that matters is the initial height and the final height. It's because that's a conservative force. All those details take care of themselves somehow. But now for the second question, we do have a non-conservative force. There is friction involved. So I'm going to start with that full version of the work energy theorem. It says that work done by non-conservative forces equals the change in potential energy plus change in kinetic energy. So the force, the non-conservative force in this case is friction. And I'll just write down how we evaluate that. Remember, work is F delta x cosine theta. It's not this theta, it's the angle between the force vector and the displacement vector. Of course, for friction, that always ends up being 180 degrees, because friction always opposes the direction you're moving. So this is minus F, the friction force, times the displacement, delta x, which we're calling this distance d. And one more step, because in this part of the motion the skier is on horizontal ground, the friction force equals mu times n, or mu times the skier's weight, mu times mg. Okay, so we have an expression for the left-hand side of this equation, and we will now write the right-hand side, the change in potential energy. Well, there is no change in potential energy on the right-hand side, because the initial height at point B is 0, the final height at point C is also 0. So if we have mg y final minus mg y initial, both of those are 0. And here's our change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And just to be clear for this problem, the initial was at location B, and V final is at location C. All those m's cancel. And the final speed here is 0. The skier comes to a rest. Okay, so with all that said, we can now finally get this expression for the distance traveled. D will equal VB squared over 2 mu G. And plugging in all those numbers, we find that the skier travels 95.2 meters before coming to a rest. So this is a situation where we're able to use a non-conservative force along with our potential and kinetic energy functions. So this was the work energy theorem. It says that the work done by any non-conservative force equals the change in energy, change in potential plus change in kinetic. And that allowed us to equate this work done by the friction force with the skier's change in energy. And in this case, the skier's change in energy was entirely a change in kinetic energy. The potential energy didn't change because they were at the same height the whole time.